This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
I particularly appreciate being invited because I'm not a paleoanthropologist and I don't really study climate specifically. Instead, what I'm going to do is give you the perspective of the other animals that occupy the Earth, these small animals, large animals, and I'm going to definitely delve us into the future and ask some tough questions about our population. So I titled my talk somewhat provocatively about tipping points, and tipping points are they're situations of a state where you have a non-linear kind of system, and when you move beyond some particular point in that non-linear system, you can't go back to where you started. And I'm going to advocate that we're poised on the edge of a tipping point for planet Earth. So when some threshold is crossed, and the question is, are we about ready to cross it or have we already? The system is going to move into a new state. And the example I put up here is an egg about ready to go off the edge. Ice melting in the Arctic might be another one to think about. So mass extinctions, I've been asked before whether or not the Earth has shown tipping points. We know they happen in ponds, they happen in small ecosystems. But mass extinctions, in fact, can happen on a planetary scale. We already saw this mass extinction graphic. They're labeled there, the Ordovician Silurian, the late Devonian, the Permo-Triassic, where we lost 95% of all the species on the planet. The Triassic, Jurassic, and the KT, where we lost dinosaurs and a lot of marine reptiles. The point is that these are mass extinctions, and you'll see in every case there's a drop in diversity. This is generic marine diversity. So this is a marine record, not a terrestrial one. But the point is that when it recovers, and it takes between 5 and 10 million years for life to recover after these mass extinctions, life is completely different. We've lost those organisms that founded the diversity on the planet prior to the extinction, and they don't come back. So it reassembles. It is, in fact, a new state. So the Earth is warming rapidly. You've seen many versions of this, but I'm providing here a little bit of a perspective from our perspective. So we're here on this graphic. All of those different colored squiggles show different scenarios depending on what models are used by IPCC. We will be here. Now, you've heard a lot about the evolution of humans, modern humans. By the time we get to that point in 2050, we will have global planetary temperatures warmer than our species has ever experienced on its time on Earth. And if we happen to make it to 2100 and to temperatures somewhat above 4 degrees, Earth has not been as hot as that projected temperature in 14 million years. Now the perspective is, and this is one I'm giving you, mammal species don't live that long. We don't have mammal species on the planet that are 14 million years old. So the memory of this climate in the genomes of these species is gone. World population is still growing. Now, there will be 9 billion people on the planet by 2045. So 2045 here, there will be 9 billion people. And if we continue at, these are current fertility rates shown in that upper blue, current fertility rates. You can imagine, 15 million people on the planet. Unbelievable. In fact, fertility rates are slowing, but not fast enough. We would have to, instead of replacing ourselves, a male and a female, with 2 children, we would have to go down to just 0.5 children per person to follow the lower blue curve. So human population growth is the elephant in the room. It is tremendously terrifying. So even though the late Quaternary transition from the Pleistocene, the cold, arid Pleistocene, to the warmer, more wetter Holocene is not exactly analogous, and in fact very different in many ways, to the kinds of climate we're experiencing today. In fact, there are 2 similar features. One, we are warming the environment as we move from the Pleistocene to the Holocene, and we're also expanding, as humans, we're colonizing the globe. So those 2 features are in fact something we share with what's happening today. So you heard a little bit about these dramatic warming and cooling events. Here's the Bowling Alley Rod, and then followed by an abrupt Younger Dryas, a cooling event that saw the extinction, for example, of Irish elk in Ireland as that environment cooled rapidly. And then we end up into what's called the Holocene, or really about the last 10,000 or so years of relatively constant temperatures. However, we expanded in this latter part of the Quaternary. We left Africa around 200,000 years ago. We colonized Europe and Asia. We colonized Australia somewhere between 40 and 60,000 years ago. And then we made it to the Americas last, somewhere between 13 and 35,000 years ago. Now, with our colonization of these isolated areas, we caused extinctions. This is a photo, this beautiful image is the menagerie of animals that used to roam in North America and are now no longer here. There are, gomphotheres, giant ground sloths, glyptodons, there's the giant bison, camels, which basically evolved in North America, left, colonized Asia, colonized South America, and went extinct in North America. And then horses, which again have millions of years of history in North America and went extinct and only to be recolonized by Spanish explorers. Historically, about half the world's large animals larger than 44 kilograms or about 100 pounds, went extinct at this time. Incidentally, humans are about that size. So it's not just our impact that cause change in animal distributions and abundance. In fact, there are some small mammals like this bog lemming that went extinct at this Pleistocene-Holocene transition. So we know that ice covered much of Canada, and there was no place for these bog lemmings to live. Every one of those black dots you see in North America were occupied by bog lemmings during the Pleistocene. They're no longer found really in the lower 48. In fact, what they are, they're occupying this orange range up here. They are really an Arctic, circumarctic species. So they responded as you'd expect a species that likes a relatively cold environment. As the ice left, they tracked that environment northwards. But not all species responded that way. These are 2 images of 2 species that are found in a cave called Samuel Cave that I excavated several years ago in Northern California, shown by the black dot there. These two species didn't really respond north. In fact, they contracted their ranges to higher elevation, but also much wetter environments that's currently found in Samwell Cave today, which is located on the shores of Lake Shasta. So these animals, the mountain beaver, it's not confined to mountains, nor is it a beaver. It is the remnant, the last species of what was a very large group of species in the family Aplodontidae, which is a very ancient North American family of rodents, and it is the only species left in the family today. It's very primitive, and it cannot concentrate its urine. And so it has to be by running fresh water all day, all the time. And so you find them confined into very dense, old-growth Douglas fir forests along the coast and the Pacific Northwest, a very ancient lineage that is threatened by warming temperatures and dry conditions. The other animal you see is the white-footed vole. Very little is known about this animal, except the fact that it's somewhat arboreal, and it's found in deciduous trees and probably up in these old-growth Doug fir forest. Again, this animal contracted with the Doug fir forest, a wetter condition, not so much higher up in elevation. Animals today are moving poleward, just like they did in the Pleistocene. This is a range map of the current distribution in 2013. The black line is the current distribution of the armadillo. The armadillo is related to that glyptodont, that giant thing I showed you in the previous slide. It's a South American animal, and it is expanding. It made it across the Rio Grande in 1850, and it's expanding northward. It's limited by winter temperatures. So if there are 24 freeze days or more, this animal can't survive. Its young can't survive. And what's happening is, as our North American climates are warming, this animal is progressively colonizing further and further north. And so what you see, not the X's, but every other symbol on this, are instances where armadillos have advanced beyond their 2013 static range. Be interesting to know where they are after this winter. However, the thing about this that I want to point out is not just that animals respond the way you predict they would based on what we know from fossils, but the other thing is this particular animal, the armadillo, is the only mammal we know about in the world that carries leprosy. And so this is an example of these unexpected synergistic things that can in fact impact humans in ways we don't anticipate. Actually, they got leprosy from us. Leprosy evolved in Asia, most likely India, and they contracted leprosy from us probably somewhere around Louisiana. But this animal can transmit leprosy to humans as well. So similarly to what I explained to you about the mountain beaver and the white-footed vole, animals will find their proper environments. And so it's not just that they move further north. As warming conditions prevail and as drying conditions prevail, they'll also move up in elevation. So many of you might have heard about the pikas. This is one of the Asian species. There are, in fact, 28 Asian species of pikas. They're related to rabbits and hares. They're just the most wonderful thing to work with. They have this enormously interesting physiology. They have a resting body temperature of about 104 degrees, and they live really high. In the Himalayas, they live above 15,000 feet. Now, the problem so we've been studying these particular animals all along the Himalayan front in India and Nepal, and it turns out that only some of these species can tolerate the hypoxic conditions that are characteristic of that high elevation. So these particular animals, and in fact, they've shown to be moving up much more rapidly than American pikas, which have moved up around 150 meters. In the Himalayas, they've moved up at least 1,000 meters, and they're pinched, right, from above because of those hypoxic conditions, and from below from warming and also human alteration of their environment. Now, another kind of unexpected example, and again to demonstrate just what ecosystems mean in terms of how species are connected. This is the map you see on the left is a map of the distribution of, on present, the whitebark pine distribution in North America. Whitebark pine is a high elevation pine. It's the last conifer that until you get to tree line. So it's the thing that you often see as crumholts in the Rocky Mountains. It's a 5-needled pine, and it has these really, really nice, calorically rich nuts in the cone. If we just look at climate models for the distribution of the whitebark pine, and you can go to 2030, 2060, and 2090, you can see by 2090 there's barely any whitebark pine left in the lower 48. Now that projection was made before we saw what happened with the mountain pine beetle. For those of you that have traveled anywhere in the Rocky Mountains, you know that in the last decade, conifer forests all the way up to tree line have been decimated. In the Yellowstone region, in some of these areas, whitebark pine are down 80%. This is a photo from one of the high elevation areas that I work in Yellowstone, and you can see a lot of standing dead trees. Now, okay, so that's because the beetle is allowed to survive over the winter. It's not killed off, it's a native beetle, but climate is definitely implicated in the expansion of this beetle. It now goes all the way up to tree line, it's not killed off, and it probably reproduces several times per year, instead of having to recolonize every year. Well, why is that? Why do I have a picture of a grizzly bear? It turns out that the number of whitebark pine cones in a tree is directly correlated with overwinter survival of adult bears and their cubs. And it's indirectly correlated with problem bears the following summer. So when there's not a lot, in some cases they may eat 40 to 50% of their fat as a result of eating these middens of cones that are mostly, again, another player in this are the Clark nutcrackers and the red squirrels here. But these grizzly bears need this to pack on the fat. And what happens is they come out of hibernation earlier and they start getting into trouble looking for food in human dwellings. So again, an unanticipated and kind of surprising but very major impact from climate change. The other thing that happens, and these are data, I'm not showing you the actual data, but during the Pleistocene-Holocene transition, there were lots of different small mammals in the Samuel Cave site in Northern California I talked about, but the animal that just took over that site is the deer mouse, Paramyscus maniculatus. And in fact, this animal has dominated the entire Holocene assemblage. So the community structure of small mammals changed. And this is not due to human hunting, this is due to the fact that there are many more disturbed environments in the Holocene. This animal has very high intrinsic rates of growth. They don't care what the environment is. They don't mind if it's just been burned. They don't mind if it's the edge of a field or if it's an old growth forest. They like disturbance. This animal is the most commonly trapped small mammal in North America. So if you lay a trap out there anywhere outside of human habitation, you're likely to catch this guy. It also tends to carry a lot of diseases. So this is a weedy species and it thrives with human environments. And the specialist species are the ones that take a nosedive. Now, I'm sure there are some of you that are gardeners here and they don't consider this pocket gopher as a particularly favorable friend in their garden. But in fact, these guys took a hit at the end of the Pleistocene. This is a pocket gopher. It has fur-lined cheek pouches and it stores its seeds and digs. In fact, this is a specialist species. It is so energetically expensive to live underground. It takes between 360 and 3,400 times the energy to do this than to move the same distance above ground. This is, by any accounts, a very specialist species. So they decline. Humans are directly causing the extinction of animals. We've lost or are threatened to lose almost a quarter of our species. I just read an article that said about a third of our bird species in Europe are threatened. Most of these are from hunting. We're about ready to see the loss of elephants in the next decade or two. 1 out of every 12 elephants was killed in just the last 3 years. This is a crisis. 51% of humans, of the terrestrial land has been co-opted for human use. The only places left on this map that aren't shown in purple are deserts and tropical forests. Those are the least easily farmed land on the planet, but they're also, in some ways, especially the tropical forests, some of the most important. Everywhere else, we have made a mark. We have an extinction debt, and we will lose a lot of biodiversity in the near future. I get asked a lot, can speciation rescue biodiversity? Absolutely not. Species take between 2 and 5 million years, this is mammal species, to evolve. So we can cause them to disappear in a decade or two, but it takes millions of years to accumulate the diversity we might have lost. So how do we avoid this tipping point, this planetary tipping point? We increased energy conversion, obviously. We stall habitat loss. We increase global cooperation. This has got to be done globally, and we stabilize population growth. And finally, how do you stabilize population growth? I get asked what is the most, in my opinion, the single most important thing for us to do is to educate women globally. And the reason is because as education goes up, fertility rate goes down. The more girls that are in school, secondary school, the number of years is really important, the more fertility rates go down. And interestingly, GDP and poverty rates also go up. Human innovation is remarkable. We can see the origin of the universe. I can't believe we can see the origin of the universe, and we can see ourselves and our beautiful planet from space. Why can't we avoid the next tipping point? Thank you.
I'm often told that my talks are very depressing, so I'm pleased to follow Liz Hadley, whose talk was even more depressing than mine. If we didn't already have enough to worry about, now we have to worry about armadillos carrying leprosy. So I was given an assignment for this meeting, and it was a very upbeat question: will we survive the future? So I'm happy to say that I actually have a positive answer to that question. The answer is yes. I do believe we will survive. As Liz just showed us, we're a much greater threat to other species than other species are to us. And short of a meteorite impact hitting us, I think that the odds that humans as a species will survive are probably very great, at least for the foreseeable future. It seems to me the more relevant question, though, is how will we survive, and particularly in what condition? Anthropogenic climate disruption and its companion threat of ocean acidification threatens to reverse the developmental gains of the past 50 years, decreasing the quality of life in wealthy nations and pushing still more of the world's poor, as well as other species, to the edge of survival. The president of the World Bank, Jim Yong Kim, has recently noted that climate change is a fundamental threat to development, one that threatens to reverse 50 years of progress. So what will a future of unmitigated climate change look like? Not just physically, but socially, economically, and politically. This was the question that Eric Conway and I set out to answer in our book that also has a very optimistic title, The Collapse of Western Civilization. The book takes place in the year 2393, when a historian looks back on our present and asks the question, how was it that they knew so much about what was happening to them, had so much good scientific information, and yet did so little to prevent it? The year is 2393. The occasion is the commemoration of the Great Collapse of 2093. I wanted to read to you from the book, but time doesn't permit that, so I'll just summarize the argument and hope that you'll go and buy the book, which only costs $6.95 in its Kindle edition. So first, our historian recounts what happened in the Great Collapse. It begins with the collapse of the West Antarctic ice sheet, and this physical collapse then ramifies into social dislocation and the collapse of economic and political systems. Then she tries to answer the why question. Why did people let this happen? And she argues that the grip of free market ideologies, combined with scientists' failure to communicate what was truly at stake, created a disabling paralysis. So my question today is, how do we avoid that future? The question of what kind of future we will have is really the question of whether we are capable of addressing the problems that are before our eyes. And this, of course, is not a new question. Indeed, I would argue it's the Malthusian question. In 1798, as most of you know, Thomas Malthus asked the question, can the Enlightenment project work? By that he meant, can we reasonably expect to improve the condition of mankind? And his short answer was no. And for this reason, Malthus is often considered an anti-Enlightenment philosopher. He rejected as impossible and even misguided the Enlightenment aspiration to achieve the perfectibility of man and of society. He even doubted the possibility of long-term and sustained improvement. Now, most of us also know why Malthus came to this pessimistic conclusion. It was what he called the positive checks, positive in the sense of absolutely positively certain. And those were the checks of famine and disease and the misery and mortality that ensued from them. Now, most of us also know that happily Malthus was wrong. And it's generally taken to be received wisdom that the main reason he was wrong was because he failed to appreciate the empowering effects of technological innovation. The 19th and 20th century saw technology enabling a number of key developments that helped to stave off the Malthusian disaster that he imagined. The most important, of course, was increased food production, but also, arguably equally important, better public health through sanitation and vaccination, which led in turn to the greater survival of children. And the survival of children, along with the education of women and the development of technologies, available technologies of population control, allowed many of the nations of the world to bring their fertility rates down without the misery or vice that Malthus feared. Because of this success, because of how much technology played a role in the development of the Western world in the last 250 to 300 years, technological success has become a foundational tenet in many of our beliefs, particularly those of us living in wealthy, industrialized, technologically endowed nations where we have benefited the most from these technological successes. Indeed, our belief in technology is so foundational that we can name several philosophies that express this belief. So, for example, technophilia, the love of technology; cornucopianism, the belief in the continued productivity of technological innovation; technofideism, or faith in technology; and more recently, something I've been calling disruptivism, a belief in the power of disruptive technologies. In fact, these philosophies are so powerful that some of them even have their own Bibles. So some of you are familiar with the Bible of cornucopianism, the book, The Resourceful Earth. Now, one of the things that I find most interesting about faith in technology is that it cuts across party and ideological lines. In fact, I would argue it's one of the few things in Western culture that does. So the cornucopians are mostly conservatives and neoliberals. They have confidence in human ingenuity and the capacity of the marketplace to do its magic. The technofideists tend to be traditional Republicans, Democrats, and what I call paleoliberals, as opposed to neoliberals. I guess we have to have meso-liberals too, but I haven't figured out who they are yet. Technofideists tend to believe in government investment in technological R&D. And then there's the disruptivists, who I haven't quite figured out what they believe in, but they talk about the need for disruptive technologies, but without specifying how those technologies come to exist. But all agree on the crucial role of technology. What they disagree about is how we get it. So liberals tend to focus on education and research, particularly in great research universities and institutions like this one and UCSD across the street. Conservatives stress free market economics and entrepreneurship, and this disruptivists don't say. But here's the rub, and actually there's several rubs. Because I'm a historian, there's never only one answer. The first rub is what I'm calling the cargo cult mentality, and we have anthropologists in the audience, so I hope they'll appreciate what I mean by this. When you listen to the advocates of technological solutions to climate change, no matter of the left, the right, or in between, one is struck by the similarity to anthropological descriptions of the cargo cult. By that I mean we are waiting for the goods to arrive, but we have no coherent plan how to get them. To the cornucopians, I would ask, well, what if the market doesn't do its magic? To the technofideists, I would ask, well, what if basic research doesn't translate into usable technologies? And to the disruptivists, what if the climate disruption arrives before the technological one? The second rub, much of this discussion ignores what we have learned or should have learned from experience. It ignores what we know from the history of technology about how transformative technologies became normal parts of our lives. Now, I live with historians, and historians don't like big generalizations. There are no laws of history, and we tend to focus on the specifics of individual developments and cases and cultures because we know they're all different. But there is a generalization that I think is broadly true about technology in the 20th century. And that is that none of the transformative technologies of the 20th century were produced either by market-based mechanisms alone or entirely by government R&D either. Rather, nearly all the transformative technologies of the 20th century involve government-private sector partnerships. And here's just a short list. I couldn't fit them all on a slide, but just some examples: rural electrification, the development of telephone and telegraph, aviation and air traffic control, nuclear power, the internet, digital computing, space technologies, pollution control technologies, all formed by government-private sector partnerships. In fact, the only two exceptions I could come up with, and being at the Salk Institute, I have to mention the polio vaccine and the contraceptive pill, also developed largely here in Southern California. These were private-private partnerships, but where one half of the partnership was philanthropic rather than private sector entrepreneurial. Electricity is a very well-studied case in point. We know a lot about the history of the development of electricity. We know that entrepreneurship brought electricity to most Americans in major cities, but it took governmental initiative to bring it to rural citizens, and that's true in other countries as well. In fact, most other countries had rural electricity before the United States did because their governments were less reluctant to get involved and because they viewed electricity as a common good rather than as a commodity. The third problem is what I'm calling the problem of persistence forecasting. And by that I mean assuming that the future will be like the past. Technology has led the way in many radical changes in the way we live, but will it be up to the challenge of anthropogenic climate change? The Zen masters have said that technology makes major contributions to the minor needs of man. Now, I think that might be a bit strong. Having a warm, safely lit house and clean water and good food would seem to be more than minor needs. But still, in a world of laptops and iPhones, one may well wonder, are we getting the technologies we want or the technologies we need? It's now a truism that Malthus was wrong, but the fact is that billions of people on Earth today do still lack adequate food and water, and they do suffer misery for that lack. And in many parts of the world, childhood mortality remains very high. Life has improved dramatically for those of us in the upper 4 billion, as I think Ramanathan calls it, but it remains highly unimproved for at least 2 billion of our fellow citizens. And in public health, it's well documented that medical breakthroughs of the past decades have mainly addressed the diseases and even the discomforts of the wealthy to the neglect of many of the most devastating diseases of the poor. So why have we made so much progress on telephones and contact lens technology and cosmetic surgery, and such relatively modest progress on solar cell efficiency and energy storage? Well, I think one part of the answer is clear. Markets respond to market signals. And without a price on carbon, there's insufficient demand for energy efficiency and storage. Governments will respond to political signals, and those have so far been largely lacking as well. And of course, this also explains why we haven't solved the diseases of the poor. And the fourth issue is the issue of inequality and inequity. Today, technological development has not resolved problems of inequality, and in some cases has, in fact, exacerbated them. So perhaps Malthus was right after all, and technology just bought us extra time. So will we survive the future? Again, I still think the answer is yes. But how we survive hangs in the balance. And it will depend in no small part on how quickly we can develop the technologies to transform our energy systems. And to do that, we can't just sit around chattering about disruptive technologies or letting the market do its magic, while meanwhile the fossil fuel industry continues to explore for and develop still more reserves of fossil fuels, including the Arctic, one of the few places on Liz's maps that is not filled with people, and of course we continue to use those fuels. We have to get past wishful thinking and techno-fideism to apply what we know from experience it is likely to take to solve these problems. And that brings me to the thorny issue of politics. people don't like to talk about politics. It's awkward and divisive. In fact, we've had a whole set of wonderful speakers here today, but no one has spoken about the evolution of political systems or the evolution of governance. But without talking about political systems and governments, I don't see how we can solve the problems that we face. Now, many people have seen an analogy between our problem of relinquishing dependency on fossil fuels and the 19th century problem of relinquishing dependency on slave labor. Interestingly, some of the people who invoke the need for disruptive technology to solve climate change are the same people who invoke this analogy with the disruption of ending slavery. But slavery was not ended because of disruptive technologies that eliminated the need for slaves. It was ended by a disruptive politics that included acts of terrorism, of illegal sheltering of escaped slaves, and finally culminated in a tragic, bloody military conflict. Now, few of us are prepared to break the law to stop disruptive climate change, and I'm not advocating that we necessarily should. And I've certainly heard many of our colleagues criticize climate scientist James Hansen for, quote, crossing a line and, quote, becoming an advocate because he has been arrested protesting the Keystone XL pipeline. I do not know whether what Hansen is doing is right or wrong, or whether it will make a difference or not, and of course no one does. But as a historian, I will say this. Most of us in the climate science arena have been focused on science and technology, and to a lesser extent on the business side of business as usual. But what may matter most, what may be most urgent, and what may actually determine the question of how we survive is whether we can create and sustain a disruptive politics. Politics makes nearly all scientists very uncomfortable. We don't want what we do to be politicized, and we are afraid of being seen as political. But it seems to me very unlikely that we can solve climate change with politics as usual. And it seems to me also very unlikely that we can solve climate change with our scientific thinking as usual either. And so maybe the time has come to think about that. Thank you very much.
We heard from Jeff Severinghaus about the greenhouse effect of carbon dioxide on Venus. And that brought me fond memories when 45 years ago, I got started in this field by taking the quantum mechanics of the carbon dioxide molecule and trying to figure out how it maintains the climate of Venus and Mars. So how did I go from quantum mechanics to talk about a topic which is totally foreign to me, in pursuit of the common good? So I have to walk you through how my science led me into the villages of India and Kenya, and finally found myself face to face with Pope Francis last year. And that's what gave me this idea of the pursuit of the common good. So let me start with a 30-second lesson on climate and climate change. The fundamental energy source for the planet is sunlight, incident solar energy. Not all of that is absorbed by the planet. The intervening clouds and ice sheets and surface bounces some of this back. So about 70% is absorbed by the planet. That heats the planet, and it gives off this energy in the infrared wavelengths. We call it heat radiation, infrared radiation. But not all of that can escape to space. The intervening atmosphere, particularly water vapor and carbon dioxide, acts like a blanket and traps this heat. In fact, the blanket is a good analog, if not a metaphor, that the blanket keeps you warm on a cold winter night, not because it gives off any heat, it traps your body heat. That's exactly how these gases trap the planet's infrared heat, which is what we call by greenhouse effect. Nature gave us a thick blanket, and later I'll tell you how thick that blanket is. So without that, the planet would be so frozen beyond anything we have seen in the ice ages, which Jeff showed us. So now, what we've been doing is adding to that blanket, making that blanket thicker. So the first of this, we heard about it, carbon dioxide, and that was worked out more than 100 years ago by Svante Arrhenius, the famous chemist. He did some of the most definitive calculations in 1896. I know this paper very well because the Swedish Academy at the 100th anniversary invited me to write a detailed critique of this. So for nearly 80 years after the publication of this paper, we thought carbon dioxide was the only molecule causing the greenhouse effect. In fact, many talks today focus on the CO2. After I finished graduate school, I stumbled on this totally shocking and surprising discovery given for myself, that we were releasing other compounds, particularly chlorofluorocarbons, CFCs, and my work showed taking again, starting from the quantum mechanics of the CFC molecule, addition of one molecule of CFC has the same greenhouse effect as adding 10 to 15,000 molecules of carbon dioxide. This is, mind you, purely synthetic gas used as refrigerants and propellants, but the CFCs were also involved in damaging the ozone layer. So the Montreal Protocol in the 1980s banned the use of chemicals after the discovery of the Antarctic ozone hole. Just in the last 5 years, my work was recognized, and the economists called the Montreal Protocol as the best climate mitigation strategy. Because my work had shown, if we had not banned CFCs, the CFC alone would have caused a 0.5 degree warming so far. Okay? So now, let me go to the real gorilla on the table, which is carbon dioxide. You know, the theory is being attacked. So the key thing is, remember, any theory is judged by its predictions. So in 1980, I teamed up with the famous meteorologist Roland Madden. We took the observed climate fluctuations, so-called noise, and said, when will we detect the signal, carbon dioxide warming? So we predicted, if the theories, Arrhenius' theory was right, we should see the warming by year 2000. As you have seen, it's after in the 1990 to 2000 period where I've shown the shade, where the warming rose above the background noise. In fact, 1,000 scientists said, finally we are seeing the human-induced warming. So there, a forecast came out to be okay. So for the last 30, 35 years, I've used varieties of instruments. The one I show on the left-hand side is the satellite, which I helped design that with 3 other scientists at NASA. We were looking at the regulation of the heat flow in and out of the planet by the atmosphere. More recently, we developed this unmanned aircraft to look at how that heating from man-made pollutants is really warming the planet. So let me walk you through. What we did was using these to track down each of the prediction by models and theories and see, are they coming to true? So the first thing we went after is what's called the water vapor feedback. Remember, I think Jeff showed, several talked about the warmer atmosphere holds more moisture. But water vapor is the most powerful greenhouse gas. So we determined the greenhouse effect directly simply by, we have estimated the infrared radiation coming from the ocean. It's basically given by the Planck's black-body law. Then we were measuring the heat escaping to the top of the atmosphere and difference the two to look at the thickness of this blanket. What you see here in the tropics is where the blanket is at its thickest. Our unit for measuring the thickness is watts of energy trapped. So why is so much greenhouse effect happening in the tropics? It's warm and humid, water vapor greenhouse effect. But we were not satisfied with that. We wanted to see, as the planet warms, would the greenhouse water vapor increase? So on the right-hand side, you see, I'm not going to go through step by step. Every year, the planet does a spectacular experiment. It's the entire planet, when you average, it's hottest during August and coldest during February. Remember, August is winter in the southern hemisphere. So when the temperature increases, we found with this satellite, the greenhouse effect increased exactly as predicted by models. And then you ask, why did that increase? That's the last bottom panel. It's because the water vapor increased as the planet temperature increased. So why is the water vapor increasing? It's basic thermodynamics. The vapor pressure of moisture above a body of water increases exponentially with temperature. So here it is. Arrhenius was the first to suggest it. The next was another theory which was done by a Russian climatologist, so-called sea ice albedo. Charlie Kennan already showed that. This took me 30 years to start from the launch of the satellite to come to this. It was one of my graduate students' thesis work. So as the Arctic sea ice retreated, what the climatologists said is, the ice absorbs only 50% of the sunlight. It bounces everything back. That's why it's white. When you melt the ice away, you get this sudden tipping point. You see the dark ocean. And we documented that exactly how much energy, and that energy increase, although it's in a tiny part of the planet, Arctic, was so large that it was equivalent to 1/4 of the greenhouse effect of CO2 increase. Okay? Again, this was suggested, but the magnitude of the feedback is much larger than what the models were using. The last one I want to mention to you, one of the key things we are after is the warmer planet going to be more cloudy? Why is that an important question? Clouds are one of the most powerful regulators of sunlight. The clouds are white because it's reflecting 50 to 70%. In our planet, both in the northern polar region, southern polar region, this massive extratropical cloud system. Remember, that's what you see when you fly across into the Pacific Atlantic, thick white. They are the refrigerants for the planet. What we are finding is, think of them as two white umbrellas. They are shrinking, letting in more sunlight into the tropical ocean, again an amplification. So when we put all of these together, remember I forecast in 1980, boldened by the success of that, we made two forecasts 7 years ago that we have already dumped enough gases to heat the planet by 2.5 degrees. We have only seen about 1/3 of it. The other thing, which is what made me go after the pursuit of the common good, said we are going to hit this 2 degrees, not what people are saying 100 years from now, around the corner, 30 to 40 years from now. Okay? So the so-called 2 degrees is facing us already. So how do we slow down the warming? Of course, most of the studies talk about cutting down CO2, which I agree with. So we came with a number to reduce the long-term warming. You've got to stabilize the CO2 below 440 ppm. CO2 is already at 400. So to limit to 440, we can't emit more than 1,000 billion tons. That looks large, but every year we are emitting 40 billion tons. So we have only 25 years left, okay? But that's not going to help the near-term warming because CO2 is like a supertanker. Its lifetime is centuries to 1,000 years. It's not going to respond quick. So remember my work on the CFCs, that's put as HC, halocarbons. That's a family of chemicals. And after that work in 1975, we came with numerous other pollutants. Ozone, it's called smog. Methane, we heard about it. The other is black carbon. It is soot, the dark stuff which comes out of diesel. It's not a greenhouse gas. It's a particle that absorbs sunlight. Much of my work with UAVs was to track that. But we have technologies to cut them down, and their lifetime is few weeks to a decade. If you eliminate black carbon from diesel, their warming effect is gone 2 weeks from now. So we said if you cut these pollutants with existing technologies, we can cut down the rate of warming in the next 30 years by nearly 50%. So you need a two-pronged strategy. So now let's look at who is going to do which. By the way, this idea of the CCAC, the short-lived climate pollutants, I wrote a paper of this for policymakers with a political scientist at UCSD that was led by Hillary Clinton. And she formed a coalition 3 years ago. Now there are 40 nations are working to cut down the short-lived pollutants. So now, let's look at the human side of the problem. For reasons I'm not going to get into, I spent, took my sabbatical and spent with my wife living in villages in India for 3 months. We also do work in Kenya. And every week or so, the life in the village was so oppressive, I would escape to the nearest city for a cold glass of beer. I have a movie I'll show if there is time. That's when I discovered, my God, there are 2 worlds in this planet. The first is inhabited by the top 1 billion, with obviously seemingly unlimited access to fossil fuels. The other world is inhabited by the bottom 3 billion, lack of access to the fossil fuels, even for cooking. They still burn firewood and cow dung. I was having my meals in this woman's house in the foothills of Himalayas. So the top 1 billion consume 50% of the energy, are responsible for something like 50 to 70% of the greenhouse gas emissions. So while population is a problem, as Dr. Hadley said, the other big gorilla is unsustainable consumption by a small part of the world's population, okay? Particularly climate change. So in terms of cutting CO2, the buzzword is decarbonization. So that takes about, it's been estimated, about $1 trillion per year. That's about $1,000 per person for the top 1 billion. And our fossil fuel subsidy is about $450 billion. So you take it out, it's basically a $500 problem we are arguing about. And then the second thing is, the worst consequences of climate change is going to be experienced by the bottom 3 billion. This woman represents about 600 million women around the world who are on subsistence farming, 1 or 2 to 5 acres. A drought like what hit California, extending for 3-4 years, would wipe them out. They would become homeless, go to slums in cities, et cetera, et cetera. So the question is, we have to give them energy access. And that has also been costed out. It's about $250 billion. So if you divide it amongst the top 1 billion, it's a $250 problem. So the question we have to ask is, why should I living here? I'm, of course, part of the top 1 billion. I'm almost on the top of the top 1 billion if you bring all my travels. So why should I give $250 to this woman sitting in Himalayas? If I don't do that, she climbs on the fossil fuel ladder. Her consumption, fossil fuel, will go up by 30%, another 12, 13 billion. So purely selfish reasons, we want to provide energy access, but we know if you throw 250 billion, it's not going to reach them, right? So we started a project called Surya, where we developed improved cook stoves to cut down the emission. In the left curve, my daughter developed cell phone technologies to measure these emissions. My instruments were all way too expensive. But this cook stove is about $70 a person. That's about 5 weeks of her paycheck, okay? So we said, she's cutting down climate by cutting down the black carbon emissions and CO2 emissions. She's saving about 5 tons a year. So if I give the minimum carbon credit to her, which is about $15, she'll get the stove paid off, and she'll be making money next 2-3 years. But how do you know she's going to use it, right? That's the biggest problem in compliance. So I went to my daughter again, asked her to do something useful. She's a wireless technology genius. So she came up with the simple temperature sensor, which hits as soon as she starts the stove, the data comes to her lab. She's at Los Angeles. She shifts to my lab. We convert it to carbon credits. UCSD created the first climate mitigation fund. And we have demonstrated it in 5,000 homes. In fact, this work was started first by donation from Qualcomm, Charlie Kennel, and a billionaire in San Francisco got it started. So next week, this methodology has been accepted by United Nations. I'll be there next in a summit. They're going to release it as one way to provide energy access. So let me go on. So I'm now taking my quantum mechanics to villages. So why did I meet the Pope? Clearly, after we heard from the last speaker and the previous speaker, I decided, by the way, I'm never going to follow Naomi Oreskes. I was so mesmerized what she was saying, I forgot what I was going to say. So we teamed up. I belong to the Pope's Academy of Science with economists, Nobel laureates in biology, physics, chemistry. In fact, Charlie and Naomi attended that summit. And we discussed this whole issue of sustainability. And at the end of it, we were asked to brief to the Pope. And I've been in this academy for every time we meet Pope, like Pope John Paul and Pope Benedict, it's always in the most ornate room in the Vatican. This Pope met us in the parking lot, right here, you say. That's why he's called People's Pope. So we briefed. What was remarkable about this group, at the end of it, 3 days of intense talks, we didn't talk about technology, we didn't talk about this. What we said was, the main way to solve this problem is to change our attitude towards nature and towards each other. And remember, by leaving 3 billion behind, they're going to suffer the consequences of our fuel consumption. And then from the previous speaker we heard, we're going to read generations of yet unborn suffering our unsustainable consumption. So it's a moral issue. So what we are saying is that religious leaders should take hold of this. And 2 weeks ago, Pope Francis, because of this previous meeting, assembled religious leaders from Islam, Hindu, Jewish, all the religions were represented. And they all signed a declaration. And anyway, so let me just come to the last point. I joined this infamous group, Planetary Boundaries Group. So we published this year this planetary boundary that is, there is a safe ecosystem, that's the inner circle. And then you exceed the outer circle, you go to the danger zone. And so there were 8 components we identified. I was the only climate scientist there. And climate change, and then the atmospheric aerosol loading is there. 2 of the components, we already exceeded the boundaries. Dr. Hadley's talk beautifully showed that, species extinction. It turns out our extinction rate is 10 to 100 times larger than when we compared to extinction rates before humans really started colonizing the planet. The other major is nitrogen. Fertilizers. We have anoxic zones in the ocean, dead, because pollutant effluents from the ocean. So climate change, there are denialists because of political and economic reasons. But our chairman also said we are also denialists. It is coded into our genes. So no matter how, if we don't do much about it, I want to conclude with my prediction that you see that the red zone, the climate was still in the yellow zone. We would exceed that by 2050, 2 degrees. So the Anthropocene, which is coined by my good friend Paul Crutzen, will reach adolescence by 2050. I'm thinking there the teenage is the most dangerous age in the human being's evolution. Right? So we'll reach 2-degree world, but I predict when we reach 2 degrees, the changes would be so huge, just physically and thermodynamically. The water vapor alone would be 15% more, fueling the storms, fueling droughts, fueling floods. So we would change our attitude towards nature. We will decarbonize the economy, but I'm saying it's a $450 problem amongst the top 1 billion. It's safe to assume all of us here belong to that prestigious club. And then we need to provide clean energy for the bottom 3 billion. Okay? Thank you very much.